Lab 5, falling slinky. Here we go. Alright, so the physics principles that we used are obviously Newton's second law to update the velocity and the position, which we've used throughout most of the labs. And this lab was very similar to the lab where we just dropped falling objects. So we have the force of drag, the force of gravity, and the force of tension. And as you can see, the slinky will behave like two separate systems when it's stretched. The top of the slinky will have the force of gravity affecting it downwards and the force of drag affecting it upwards, while the bottom will only have the force of tension and the force of gravity, which will cancel out, leaving the slinky sort of like in a floating manner. We'll explore this later. Now, once the slinky compresses and it becomes one, like the system axis one, then the slinky will have the force of gravity and the force of drag acting on it. Alright, so how did we set up this experiment? Basically, I took a recording of this dude dropping his slinky, and I analyzed it using Tracker, and we set our initial conditions to the mass of a slinky. There was no velocity, and and the initial position was, we took it to be 0, 0. So basically, we just used two mass tracking controls to measure the distance traveled, one by the top of the slinky and one by the bottom of the slinky. And then we created a code that reflects the experiment to see how close the experiment was. We compared these two later, and we'll see what the conclusion was. Alright, so here's the code. I know it's a little hard to see, but basically, all you gotta take from this is that there's two while loops, and the first while loop is while the time is less than about 1.43 seconds. Basically, this is the time that it takes for the slinky to compress. So this would be analyzing the motion of the top of the slinky. So basically, just the motion of the top of the slinky. And the second while loop is while t is less than 2.33 seconds. This is the time that it takes for the total slinky to hit the ground. This will be analyzing the slinky as a whole. And basically, as you can see, there are two forces that contribute towards the net force. It's the force of the weight and the force of the tension, while the slinky is not compressed. But while it's compressed, we have the force of drag and the force of gravity, which is what we already mentioned before. Alright, so I know that may be a little confusing, but here are results. So we have two position versus time charts, and the one on the left is the position versus time of the bottom of the slinky, while the one on the right is the top of the slinky. Now, as we can see, the one on the left has that the velocity of the bottom of the slinky remains stationary until the slinky acts as one, right? So until it collides. So that's why there is no change in position. And the position of the top of the slinky is a linear graph almost that shows that, it's being compressed. And the red shows that the top and the bottom follow the same position over time, aka the velocity. So once they compress, they fall with the same velocity. And as you can see, our Glowscript code sort of coded the same thing. So, to conclude, what does all of this pieces of information mean? So basically, this means that the forces acting on the bottom of the slinky consist of the force of the tension and the force of gravity, which are equal in magnitude and therefore sort of cancel out, which is what gives a floating effect. Now, once there's an amount of time that it takes for the top of the slinky to reach the bottom of the slinky and act as a whole, right? So that amount of time is the time that it seems like it's floating. Now, once the system actually gets compressed, the system acts as a whole with the force of gravity acting down and the force of drag acting upwards. And this just behaves like a normal falling object. So yeah, that's basically the explanation of why a slinky seems to float on the bottom until it hits one. Basically because the force of tension and the force of gravity at the bottom cancel out until the slinky acts as a whole. So thank you for listening to my fifth lab, and I'm doing this from my house with AirPods, so I know the audio is a little bad, but thank you for listening, and yeah, thank you.